Okay, 5.6 is on the ratio and root tests. Okay, and this will finish this up on the tests for convergence. Okay, 5.1 through 5.6 are the tests for convergence. Okay, basically 5.2 to 5.6. Okay, and we've covered 10 tests. We'll go over all 10 of them at the very end as kind of a recap. Okay, so let's do a definition. Okay, a series, okay, the summation of a sub n is absolutely convergent if the series of the absolute values or what we call summation absolute value a sub n. It means that we're taking the absolute value of every term. It means that even if it's alternating, we stop the alternation and we kind of negate the alteration. We just let every term be positive. Okay, so this is absolutely convergent if the series of the absolute values converges. Okay, thank you, Angel. Okay, let's do an example of this. The series, okay, summation as n equals 1 to infinity of -1 to the n minus 1 over 1 over n squared is absolutely convergent. Okay, is absolutely convergent. Okay, it is convergent. This original series is convergent by the alternating series test, but it is also absolutely convergent. Okay, because when I take the absolute value of all the terms, it kind of gets rid of this alternating -1. If we say that n equals 1 to infinity of -1 to the n minus 1 of 1 over n squared, absolute value, that's going to be the same as just taking n equals 1 to infinity of 1 over n squared, okay, which is itself a convergent P series. Okay, with P equal 2, which is greater than 1. Okay, so it converges. Okay, so not only was this alternating series convergent, and we could prove that by the alternating series test, the absolute value of the terms, again, let me show you what this looks like. If we took the alternating series, okay, and the absolute value series, okay, my first term for the alternating series would be 1, and then I'd go a minus 1 over 2 squared, which is 4, plus a 1 over 3 squared, which is 9, minus 1 over 4 squared, which is 16, plus 1 over 25, ... The terms are getting smaller. Every term is smaller than the one before it. So this converges by the alternating series test. Okay, but if we take the absolute value of each of these terms, okay, we absolute value every single one of these terms, we still get a convergent series. Okay, this is P series. And so we say that it converges absolutely. Now, it is harder to get absolute convergence than just convergence. Okay, so think of it this way. Think of it like maybe a Venn diagram. Okay, this is convergent. And then inside it is absolute convergence. Okay. Okay, so absolute convergence, harder to get. But here's the thing. But if we get absolute convergence, we get convergence for free. Okay, but absolute convergence implies convergence. Okay, so if we take the absolute value of the terms, okay, and we get something that's convergent, well, then the original series was convergent. So if we can prove absolute convergence, then we get convergence for free. Okay. Okay, can something be convergent but not absolutely convergent? Absolutely. Okay, if we take the series, we'll call this example 2, the series of the alternating harmonic series, n equals 1 to infinity. Okay, this is convergent by the alternating series test. Okay, but when I take the absolute value of every term, what do I get? If I take the absolute value of each of these terms, what would I end up with?
The absolute value of 1 over n.
Okay, close. N is always positive, so do we really need the absolute value? So if we take the absolute value, we'll get rid of the alternating, and the absolute value of 1 over n is just 1 over n. So this is the series n equals 1 to infinity of 1 over n. What do we know about that series?
It's a harmonic series?
Yeah, thank you, Grace. It's our harmonic. And what do we know about the harmonic series?
It diverges.
It diverges, exactly. Thank you. Thank you, Jose. Okay, the harmonic series which diverges. Okay, so we say that the original series or we call the we could say so we call the original series summation n equals 1 to infinity of negative 1 to the n minus 1, 1 over n, we call that conditionally convergent. It's convergent, but it's not absolute. Not absolute. Okay, if it converges, but the absolute values don't converge, we call that conditionally convergent. Okay, let's do a formal definition of this. A series, A sub n.
I didn't get that. Could you try again?
This is why I always have to turn my phone off when I talk about this chapter. Okay, a series, not theory, okay, is is called conditionally convergent. Okay. If it is convergent, but not absolutely convergent. Okay. So absolute convergence implies convergence. Okay, if we prove that something is absolutely convergent, we get convergence for free. Okay, but if something's convergent, that does not imply absolute convergence because it could be conditional. Okay, it could be conditional. Okay. Okay, number 3. Okay, determine if the series summation n equals 1 to infinity of cosine n over n is convergent or divergent. Okay. So let's look at the series n equals 1 to infinity of, this is cosine 1 over 1. Whoops, sorry. This is cosine n over n equals cosine 1 over 1 plus cosine 2 over 2 plus cosine 3 over 3 plus cosine 4 over 4 plus dot, 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 dot. Okay. So what do we know about these values? Cosine 1, cosine 2, cosine 3, cosine 4. Well, first let's ask the question, are those in radians or degrees?
They are radians.
Yeah, very good. They are in radians. Okay, the default value for trigonometric functions is radians. Okay, so they are in radians. Good job. Okay, so they're in radians. What do we know about the range of cosine? Where does it go from? If I were to look at the cosine of n's, what value is it kind of bounded between?
A 1 and 0?
Negative 1 and 1.
Yeah, thank you, Daniel. Yeah, negative 1 and 1. The cosine function, it's going to go along and it's going to bounce up and down, and it's going to be bounded between negative 1 and 1. Does that make sense? Okay. So I'm going to rewrite this. I'm going to rewrite this here as the absolute value of cosine n is less than or equal to 1. Okay. And I made a typo here. This should be n squared. So this is 2 squared, 3 squared, 4 squared. My bad. So so what I can do here is I can say that, and then let's divide this by n squared, both sides by n squared. So what I can say is that this absolute value of cosine n over n squared is less than or equal to 1 over n squared, okay? Okay, so what we're gonna try to prove here is absolute convergence, and then we'll get convergence. Okay, is this thing absolutely convergent? Is the sum over n equals 1 to infinity of cosine n over n squared, is that thing absolutely convergent? Okay, well, this is equal to n equals 1 to infinity of the absolute value of cosine n over n squared. And we're saying that this thing is less than or equal to, okay, less than or equal to the sum of n equals 1 to infinity of 1 over n squared. Okay. Okay, what do we know about this series here? Summation as n equals 1 of 1 over n squared. What do we know about that series? This is a p series. Okay, n is equal, or p equals 2. Okay, and so does that converge or diverge?
Converge.
Yeah, it converges. So this converges. Okay, it's a convergent p series. And again, if I know that a series converges, but every term is less than or equal to that term, okay, what do I know? Okay, if this is, say, a known convergent series, and I want to compare it to b sub n, which is always smaller than a known convergent series, this thing is known to converge. Then what can we say about what we have here? Well, then we know that that converges, right? And what is this called? What test did I use there? Okay, comparison test. Okay, so by the comparison test, okay, all these cosine values are going to be less than or equal to, the absolute value of all the cosine values are going to be less than or equal to 1. So when I add all this up, okay, I'm going to get, okay, terms that are smaller than the other guy's terms, the 1 over n squared. By the comparison test, the summation n equals 1 to infinity of this absolute value of cosine n over n squared, okay, is convergent. Therefore, what do we know? Therefore, we know that the original, which could have had negative values, which would make the sum even smaller. Therefore, n equals 1 to infinity of cosine n is what we call, n over n is what we call absolutely convergent. And thus convergent. Okay, so that guy is in fact convergent. Okay, the original that we wanted. Okay, way back here. This thing will converge. Because some of these cosine values will be positive, some will be negative, but none of them will be bigger than 1. Okay, greater than, none of them will be greater than 1. So we can compare it to a normal unknown P series, and it will converge. Okay, not only is it absolutely convergent, it is therefore then just convergent. So we get convergent as our answer. Okay, the ratio test. Okay, ratio test, probably one of the more powerful tests out there. Okay, I always kind of look at some series, and ratio test is right up there at the top of my tools. I'll say, hey, is that going to be good for the ratio test? And I'll just go right to the ratio test. It's kind of my first one that I go to. If that doesn't work, then I'll go to something else. But if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is equal to some L, to some limit, and that limit is less than 1, okay? Okay, then the series summation of a sub n equals 1 to infinity, is absolutely convergent. So what we're testing here is absolute convergence. It is absolutely convergent, okay, and thus convergent. Okay, so I'll get absolute convergence, which will tell me that it is therefore convergent. Okay, now the original thing could be convergent, and if it fails the ratio test, it still could be convergent. It could just be conditionally convergent. We don't know at that point. But if we get a limit that is less than 1, we know that's absolutely convergent. That's great, and a lot of things will be absolutely convergent. Okay, if the limit as n goes to infinity of a sub n plus 1, that's the nth plus 1 term, over the nth term, this ratio, the absolute value of this ratio, if that equals some limit L, and that is greater than 1, then the series is divergent. The series, I should say a sub n, the series a sub n is divergent. If the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to L is equal to 1, then the test is inconclusive. Okay, and then we just choose a different test. Okay, so if it equals 1, it's inconclusive. We're going to choose a different test. Okay, so let's do a couple of these. Okay, number 4. Test the series okay, summation n equals 1 to infinity of negative 1 to the nth power n cubed over 3 to the n for convergence. Okay. The limit as n goes to infinity of negative 1 to the n plus 1. Okay, so I'm going to take this series here and I'm going to do the n plus 1th term. So this is going to be a sub n plus 1 over a sub n. So wherever I see an n, I'm going to replace it with an n plus 1. This is going to become n plus 1 cubed over 3 to the n plus 1 power. Now this is going to be a complex fraction. Okay, and so that's all going to be over. Oops. Okay, the original. And the original is negative 1 to the n cubed over 3 to the n. Now, since I have a fraction over fraction, I can flip and multiply the bottom one. Fractions, dividing fractions can be fun when you flip and multiply the bottom one. Okay, so negative 1 to the n plus 1. Okay, times n plus 1 cubed, all over 3 to the n plus 1. Okay, times, this is going to flip upside down, 3 over n, 3 to the nth, negative 1 to the nth, and n cubed. Okay. So now I'm going to kind of put the like expressions together. Okay, ones that look like each other, I'm going to put on top and bottom and see what happens. Limit as n goes to infinity of negative 1 to the n plus 1. Okay, all over negative 1 to the n times 3 to the n over 3 to the n plus 1 times, okay, n plus 1 cubed over n cubed. Okay. Okay. If I have negative 1 to the n plus 1 over divided by negative 1, then the n plus 1 goes n plus 1 minus n. Okay, so this is equal to the limit as n goes to infinity of negative 1 to the n plus 1 minus n. So those cancel out. The 3's go to 3 to the n minus n plus 1. Okay, and then these guys, I can put all of these, because they're both being cubed, n plus 1 over n, and then cube that absolute value. Okay. Nice. Nice. Okay, so this thing just becomes absolute value. Oops. Oops. I think I lost my Zoom for a second. Come on, come back. Okay. Zoom, zoom, zoom. Bring this back. Okay, so this becomes negative 1 to the first power. This is going to become, distribute the negative sign, 3 to the negative 1. Okay, and then this is going to become n plus 1 over n cubed. Okay, again, limit this over here. Okay, limit as n goes to infinity. Okay, so this is -1 to the first over 3 to the negative first. This is -1/3, okay? Times n plus 1 over n cubed, absolute value of that, equals the limit as n goes to infinity, okay? I can break this apart. Absolute value of -1/3 times the absolute value of n plus 1 over n cubed. Okay. Limit as n goes to infinity. The absolute value of -1/3 is just 1/3. N plus 1 over n, I can divide both top and bottom by n. And what I'll get is I'll get n plus 1 over n all over n. Okay. Absolute value. We can really remove the absolute values if we want to, but I won't do it just yet. Okay. Cubed. So this becomes 1 plus 1 over n over 1. Cubed. Absolute value 1/3. Limit as n goes to infinity. Limit as n goes to infinity. Now we can take the limit as n goes to infinity. This goes to 0. This whole thing goes to 1. And so 1 times 1/3 is just 1/3. And since 1/3 is less than 1, this thing converges absolutely. Okay. Therefore, okay, the original series, n equals 1 to infinity of -1 to the nth power times n cubed over 3 to the nth converges. Okay. It converges. Okay, it is absolutely convergent, therefore it is convergent. Okay, because we got a value less than 1. Okay, let's try another one. Okay, let's try this series, the summation n equals 1 to infinity of 1 over n. Hopefully everybody knows what factorial means, but if you don't, n factorial, okay, for example, if I have a 5 factorial, that's 5 times 4 times 3 times 2 times 1. N factorial is n times n minus 1 times n minus 2 times n minus 3 all the way down to 3, 2, 1. Okay, we're just multiplying all those together. Okay, so the ratio test works really good with factorials, and we're going to see why. Because when we do the ratio test with factorials, a bunch of stuff cancels out. Okay, so test the series for convergence. So now we're going to say, okay, the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to the limit as n goes to infinity of 1 over n plus 1 factorial all over 1 over n factorial. Okay. Okay. So this becomes the limit as n goes to infinity of flipping and multiplying, we get n factorial over n plus 1 factorial. Okay. So this equals the limit as n goes to infinity of n times n minus 1 times n minus 2 dot, 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 3, 2, 1. That's what n factorial means. This here is going to be n plus 1 times n minus 1 times n minus 2 dot, 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 3, 2, 1. I don't need parentheses. Okay, and so what cancels here is everything but the, okay, n plus 1. So we get the limit as n goes to infinity of the absolute value of 1 over n plus 1, this thing is going to go to 0 because it's going to be 1 over infinity, which is 0. So this thing equals 0, which is less than 1. Okay, therefore, the original series summation of 1 over n factorial n equals 1 to infinity is convergent. Okay, it's absolutely convergent. Okay, in this case, that wasn't really the point. Okay, we don't have anything alternating, so the original series and the absolute values are the same. But why we use the ratio test here was because of the factorials. Okay, again, the ratio test works really, really well if we have factorials. Okay, and so the series is therefore convergent. It's absolutely convergent as well, but we don't really care about the absolute convergency. It's because it's not alternating, but this guy is convergent, okay, by the ratio test. Okay, so once again, tell me which test you used. Okay. Okay, let's talk about our last test. Okay, let's talk about our last test here. Our last test is called the root test. Okay. Okay. Very similar to the ratio test, but it's for the nth root. Okay, square roots, cube roots, fourth roots, okay, 25th roots. If the limit as n goes to infinity of the nth root of the absolute value of a sub n, so this is for the nth root, is equal to some limit, which is less than 1, then the series okay, summation a sub n is absolutely convergent okay, thus convergent. Okay. If the limit as n goes to infinity of the nth root of, sorry, this was a sub n to the nth, my bad. There should be an n there. Does there need to be an n? No, there doesn't need to be an n there. I'm sorry, I misspoke. It's just absolute value of a sub n because the series will have you're generally going to use this if the series has an exponent of n. Okay, so it's just a sub n. Okay. Okay, if this limit is equal to L and is greater than 1, then the series diverges. Okay, if the limit as n goes to infinity of a sub n equals L equals 1, then the series is inconclusive. Choose a different test. Now we have 10 to choose from, so we could choose one of the other 9. Okay, so let's do an example with the root test. Okay, let's test the series. Summation n equals 1 to infinity of 2n plus 3 over 3n plus 2 to the nth power for convergence. Okay, let's test this for convergence. Okay, so let's take the nth root here. The limit as n goes to infinity of the nth root of this guy, 2n plus 3 over 3n plus 2 to the nth power absolute value. Okay. That is the same thing as the limit as n goes to infinity of the nth root of the absolute value of 2n plus 3 over 3n plus 2 to the nth power. And now these are going to cancel each other out. And I'm just left with the limit as n goes to infinity of the absolute value of 2n plus 3 over 3n plus 2. Okay, and then if I use L'Hopital's rule on that, okay, I get the limit as n goes to infinity of 2 over 3, which is equal to 2/3, which is less than 1. Therefore, by the root test, the series summation n equals 1 to infinity of 2 to the n plus 3 over 3n plus 2 to the nth power is convergent. It's absolutely convergent, which makes it convergent. Okay. Okay. Let's do a summary of these tests. Okay, let's summarize all of these tests. Okay, and then let's look at a last example here. Okay, summary of tests from sections 5.2 to 5.6. So 5 seconds. Okay, tests for convergence or divergence. Test for convergence or divergence. Okay, the first one that we talked about was the geometric series. Okay, and if we get a common ratio r, absolute value of r less than 1, then the series is convergent. Okay, if the common ratio, the thing that I'm multiplying by each time is less than 1, it's a convergent series, and it actually converges to a1 over 1 minus r. Okay, number 2, the second thing that we talked about was the harmonic series. Okay, which is the summation of 1 over n. Okay, and as n equals 1 to infinity. And this thing is always divergent. And we showed it a couple of different ways. We took the integral, we did it algebraically, and that thing is divergent. Okay, the third thing that we talked about was the divergence test. Okay, or the nth term test, as it's called in some other books. Okay, and this says that if the limit as n goes to infinity of a sub n does not equal 0, meaning that it's not decreasing, then it is divergent. Okay. Okay, number 4. Okay, it is the integral test. Actually, number 4 is actually P series. So let's talk about P series. Okay, P series test. Okay, if the summation, or if say we get the summation n equals 1 of 1 over n to the p, where p is less than 1, okay, it is, well, p is, let's say p is greater than 1, then it's convergent. Otherwise, p greater than or equal to 1, divergent. Okay. If p is equal to 1, it diverges, and if p is greater than, oh, sorry, less than or equal to, I should say less than or equal to there. Okay, and if p is less than 1, then it diverges. Okay, number 5. What do we got? Integral test. Okay, so the integral test says if I go from 1 to infinity, okay, of a sub n, well, how do I want to phrase this? Okay, if the integral 1 to infinity of f of x dx, okay, is convergent, and f of n equals a sub n, then the summation of a sub n is also convergent. Okay, if the integral 1 to infinity of f of x dx is convergent, and f of n equals a sub n, or sorry, is divergent, and f of n equals a sub n, then the original series is also divergent. Okay, so that was integral test. Okay, the next one is basic comparison test, I believe. No. Yeah, basic comparison test. Okay, so we'll just call this the comparison test. Okay, sometimes it's called basic. Move this over. Okay, in our text, this is called the comparison test. Okay, if b sub n is convergent, okay, and a sub n is less or equal to b sub n for all n, then a sub n is convergent. If a sub n is divergent, and a sub n is less or equal to b sub n for all n, then b sub n is divergent. Okay, that's the basic comparison test. Number 7 is the limit comparison test. Okay, so the limit comparison test says that if we take the limit as n goes to infinity of a sub n over b sub n, and that is equal to some constant greater than 0, write it out, then either both a sub n and b sub n diverge, or both converge. Okay, number 8. Okay, is the alternating series test. Okay. And this says that if we have the summation n equals 1 to infinity of -1 to the n minus 1 a sub n, okay, we'll call that b sub n actually, b sub n, okay, this is convergent if and only if, one, the terms are decreasing, and two, the limit as n goes to infinity of b sub n is equal to 0. Okay, if this is true, if these are both true, then it converges. Okay. Okay, number 9, covered that today. That's the ratio test. Okay, and the ratio test says the limit as n goes to infinity of a sub n plus 1 over a sub n. If this is equal to some limit, and this is less than 1, then the summation a sub n is convergent. Okay, if the limit n goes to infinity of a sub n plus 1 over a sub n is greater than 1, then the original series is divergent. And if it equals 1, it's inconclusive. Okay, and then the root test. Okay, the limit as n goes to infinity of the nth root of the absolute value of a sub n, if that is less than 1, then the original series is convergent. And if the limit as n goes to infinity of the nth root of a sub n is greater than 1, then a sub n is divergent. Okay, and that's all 10 tests. Okay, so all 10 tests, kind of in a nutshell, okay, are right here. Okay, summary of all the tests, okay, that we've covered. Now, on the exam, it's going to say, hey, here's a series, choose a test, and test for convergence. And there may be one or two or three tests that you could use to test for convergency. There may be one that's easier than the other, but it's entirely your choice. Okay. On some of them, I'll just say, hey, use this test, use the alternating series test to test this. Okay, but some of them I'll leave that up to your choice. Okay, so let's do an example here. Okay, which test should we use? Okay, let's play the game. Which test should we use? Okay, so I'm gonna put a series here. Let's do n minus 1 over 2n minus 1, or 2n plus 1. Okay, n equals 1 to infinity. Which test should we use here? Any ideas? Which test should we use to show whether or not this is convergent or divergent? Any ideas? Yeah, this one's not as straightforward, but if we took the limit of a sub n, if we took the limit as n goes to infinity of a sub n, we would get 1/2. Which is not equal to 0. And so what does that tell me? It diverges by the divergence test. Okay, does that make sense? So so I would have used the divergence test on this. Just take the limit of that thing, and if it doesn't go to 0, then it's not going to converge. Okay, so we might want to try that one first on things. Okay, what about the next one here? Summation n equals 1 to infinity of the square root of n cubed plus 1 over 3n cubed plus 4n squared plus 2. Okay. Well, in this case, I'm going to look at just the first terms. I'm going to say that this is equivalent to another expression, one that's a little less complicated. It's not equivalent or equal. It's comparatively similar to n cubed over 3n cubed. Okay. So we can compare this to this guy, n equals 1 to infinity. This thing becomes n to the 3/2. Let me give myself some more room. Okay, this becomes, this is now equal to, okay, n to the 3/2 over 3 to the n to the 3rd. N to the 3/2 over 3n to the 3rd, that's going to be a negative 3/2 when I reconcile those. And so this is just going to become n equals 1 to infinity of 1 over 3n to the 3/2. That is a convergent p-series. And so we would do the limit. We could do limit comparison on this or just basic comparison, either way. Okay, I would actually do limit comparison because of this complicated numerator. So I would do limit comparison on this. Limit comparison. Okay, to something a little less complicated, but I know converges. Okay. C, summation of n equals 1 to infinity of n to the e to the negative n squared. What could I use here that would be fairly straightforward? Any ideas? And don't say the ratio test, because that's not the one that's straightforward here. Okay, it's actually the integral test. That's the easiest to do here because I can get an easy u du substitution. Negative n squared becomes negative 2n, okay? Or negative x squared becomes negative 2x dx, okay? And so I can get an easy u substitution. We can show this thing converges, the integral converges, and therefore the original series converges. So integral test on that one. Okay, u is equal to x squared. Okay, so du is equal to 2x dx. Okay. Okay, let's do a few more of these. D, summation n equals 1 to infinity of negative 1 to the nth power over n cubed over n to the 4th plus 1. Okay, any ideas on what test we might want to use for this one?
Alternating?
Yeah, alternating series test. Very good. Thank you, Grace. Alternating series test. Okay, alternating series test. Okay, E. Okay, E. Okay, let's look at this one. Okay, summation n equals 1 to infinity of 1 over 2 plus 3 to the nth power. What one might I want to use on this one? Okay, well, if I get rid of the plus 2 here, I get another series, which looks like this, 1 over 3 to the nth power. Okay, that looks very similar to this, n equals 1 to infinity of 1 over 3 to the nth power. Okay, I could use a root test on this if I really wanted to, and then compare that to the original. Okay, or I could see that this thing is geometric series with r, absolute value of r less than 1. Okay, where 1/3 is less than 1. Okay, so this converges. Therefore, we're going to compare this guy to this guy. And the inequality goes the correct way. Because if I have 3 to the nth plus 2, 1 over 2 plus 3 to the n is less than or equal to 1 over 3 to the n for every single term for all n. And so the inequality goes the correct way. Okay, we have something that is smaller than a known convergent series. And so we're going to use the basic comparison test here. Okay, comparison test. Okay, let's try one last one here. Okay, if we have the summation of n equals 1 to infinity of 2 to the k over k factorial, let's do k in this case. K equals 1, k factorial. What's kind of my go-to on this one? Okay, what does this have in it that should scream to you what test I'm going to use?
The ratio test?
Yeah, thank you, Daniel. The ratio test. It has a factorial. Okay, so it kind of screams out, use the ratio test. Okay. Okay, and that's it for 5.6.